In the last two modules, we have considered the problem of testing theta theta naught against theta greater than theta naught for uniform 0 theta population, and we have shown that there are several uniformly most powerful tests for this problem. We have also considered the problem of testing composite null like theta is less than or equal to theta naught against theta greater than theta naught, and there are several uniformly most powerful tests for this problem also. In this module, we want to find uniformly most powerful test for testing theta theta naught against theta less than theta naught. So, if we can show the test which is uniformly most powerful for testing theta theta naught against theta greater than theta naught is also uniformly most powerful for testing theta theta naught against theta less than theta naught, then that test is uniformly most powerful for testing theta theta naught against theta not equal to theta naught. In the last module, we have shown that this psi is uniformly most powerful for testing theta theta naught against theta greater than theta naught for uniform 0 theta problem, and we have also seen that this psi is not uniformly most powerful for testing h naught prime theta is less than or equal to theta naught against theta greater than theta. However, as we shall see, this psi is uniformly most powerful for testing theta theta naught against theta not equal to theta naught. We have already considered the problem against theta greater than theta naught, now theta theta naught against theta less than theta naught, and if we can show that this psi, we have already shown that this is uniformly most powerful against theta greater than theta naught, this is uniformly most powerful against theta not equal to theta naught. Now, start with theta theta naught against theta theta 2, two simple hypotheses. So, simple null against simple alternative and use Neyman-Pearson lemma. But here theta 2 is less than theta naught. Our aim is to find a most powerful test for this problem. So, see this figure. So, consider N2, and here the region in yellow is the sample space under the alternative theta theta 2, because theta 2 is less than theta naught. Now, mathematically the pink region is set of x for which x order n, that is maximum of x1 x2 xn, lies between theta 2 and theta naught, and yellow region is x order n is less than or equal to theta 2. So, y union p, the big square, that is the sample space under null hypothesis theta theta naught. Now, we want to derive most powerful test for this problem. So, p theta 2x is 1 by theta 2 to the power n if x order n is less than or equal to theta 2 and 0 otherwise, and k p theta naught is k by theta naught to the power n if x order n is less than or equal to theta naught and 0 otherwise. You can take k less than this or greater than this and try to find most powerful test for this problem, but here we consider that k is exactly theta naught by theta 2 to the power n. Now, p theta 2 greater than k p theta naught is equivalent to p theta 2 1 by theta 2 to the power n, and k p theta naught is 0. That is, p theta 2 is positive and k p theta naught is 0. That is, p theta naught is 0, and which is equivalent to x order n is less than or equal to theta 2 and x order n is greater than theta. But you see, thus theta 2 is less than theta naught. So, simultaneously less than theta 2 and greater than theta 2 theta naught. So, you see the regions and both inequalities cannot simultaneously hold. Next, p theta 2 is less than k p theta. P theta 2 is 0 and k p theta naught, k by theta naught to the power n. P theta 2 0 and k p theta naught, k by theta naught to the power n is equivalent to x order n lies between theta 1 to theta naught, and the region in violet depicts what the inequality is above say. By the Neyman-Pearson lemma, most powerful level alpha test for testing theta theta naught against theta theta 2 is of the form phi star, which is 0, because if x order n lies between theta 2 to theta naught, p theta 2 is less than k p theta naught. Therefore, phi star x must be 0 in that region, and otherwise p theta 2 and k p theta naught are same. So, that is the region where you can take phi star any value between 0 and 1. So, x order n greater than theta naught and simultaneously x order n is less than or equal to theta 2, and psi condition, that is expected value of theta naught under phi star, that must be alpha. So, we consider this phi star x like, so phi star x is 0 if x order n lies between theta 2 and theta naught and any value the remaining region. So, take phi star as 0 if x order n lies between theta naught alpha to the power 1 by n to theta 2 and 1 otherwise. Here we have to assume that theta 2 is greater than theta naught alpha to the power 1 by n. Now, combining these first two cases, we can rewrite this as phi star is 0 if x order n lies between theta naught alpha to the power 1 by n to theta naught, and 1 if x order n greater than theta naught or x order n is less than or equal to theta naught alpha to the power 1 by n. You see that theta 2 is not present here. So, we remove theta 2 by considering this region x order n lies between theta naught alpha to the power 1 by n to theta 2 and take phi star 0 there. Okay? So, phi star is 0 if x order n lies between theta naught alpha to the power 1 by n to theta naught and 1 otherwise. Now, we show that psi is indeed uniformly most powerful for testing h naught against h 2 theta less than theta naught. If in the last slide we see that if the theta is greater than theta naught alpha to the power 1 by n, then phi star, which is most powerful for testing theta theta naught against theta theta 2, is free from theta 2. Therefore, this phi star is uniformly most powerful for testing theta theta naught against theta less than theta naught, but this theta 2 is definitely greater than theta naught alpha to the power 1 by n. So, we cannot say that this is uniformly most powerful test against theta less than theta naught. So, here we can say that this test psi is uniformly most powerful at level alpha for testing h naught against theta lies between theta naught alpha to the power 1 by n and theta naught, because this condition is essential that theta 2, so any theta 2 lies between this, we have psi as uniformly most powerful test. Now, for theta 2 by theta naught to the power n is less than alpha, then we have already shown that power of psi is 1 for every theta less than theta naught alpha to the power 1 by n. So, here theta 2 is less than theta naught alpha to the power 1 by n. We have already considered the case where theta 2 lies between theta naught alpha to the power 1 by n to theta naught, but for theta 2 less than theta naught alpha to the power 1 by n, the power is 1. So, that is obviously uniformly most powerful for testing H naught against theta less than theta naught alpha to the power 1 by n. So, we have shown that this H naught theta theta naught against theta less than theta naught alpha to the power 1 by n. This problem is tackled using the power function of psi that we have already shown, because the power is 1. It is possible to identify a constant k such that an application of the Lehmann-Pearson lemma gives the most powerful test for testing H naught against without any reference to the power. Can you guess what that constant is? Thus, psi is uniformly most powerful at level alpha for testing H naught, theta is theta naught against both H3, that theta lies between alpha to the power 1 by n into theta naught to theta naught, and theta less than theta naught alpha to the power 1 by n. We can say that psi is uniformly most powerful at level alpha for testing theta theta naught against theta less than theta naught. We have already shown that this psi is uniformly most powerful at level alpha for testing theta theta naught against theta greater than theta naught. Here we have shown that this test psi is uniformly most powerful at level alpha for testing theta theta naught against theta less than theta naught. So, combining these two, we get that this psi is uniformly most powerful at level alpha for testing H naught theta theta naught against theta is not equal to theta. So, we have derived a uniformly most powerful test for testing against two-sided alternatives, and we can show that this uniformly most powerful test psi is unique. So, in this case, for the uniformly 0 theta problem, we have obtained a uniformly most powerful test, and we can show that that is unique, and this however is a rare instance of the situation where a uniformly most powerful test against two-sided alternative exists. Suppose x1, x2, xn is a random sample from normal distribution with mean mu and variance 1. It is a simple problem. You can find uniformly most powerful test for testing mu naught against mu greater than mu naught, uniformly most powerful test for testing mu naught against mu less than mu naught. So, mu less than mu naught, mu greater than mu naught, uniformly most powerful tests are available, but they are entirely different. So, you cannot find uniformly most powerful test for testing mu naught against mu not equal to mu naught. But here you find uniformly most powerful test against two-sided alternative. Another situation where uniformly most powerful test for H naught theta theta naught against two-sided alternative exists. The exponential is form e to the power minus x minus theta if x greater than theta and 0 otherwise. How can we solve this? You can solve it using Neyman-Pearson lemma directly, or if somehow the exponential distribution can be transformed to uniform 0 theta prime distribution, then our problem would reduce to the case discussed. Can you think of some function g such that if x follows this distribution, gx follows uniform 0 theta dash? If this is possible, then if you have a random sample x1, x2, xn from this distribution, then gx1, gx2, gxn is a random sample from uniform 0 theta prime distribution, and you can definitely solve that problem using this uniform distribution population problem. So, it can be easily solved. Now, another way you can solve this uniform distribution problem, uniform 0 theta problem, by using the optimization technique. So, you have to find phi such that E theta phi is maximized for every theta not equal to theta naught, subject to expected value of phi under theta naught is less than or equal to alpha. Since x order n, that is maximum of x1, x2, xn is sufficient for theta, you can use the distribution of x order n, and from there you can find the uniformly most powerful test for testing theta naught against theta not equal to theta naught. You can try that. In this module, we have shown that there exists a uniformly most powerful test at level alpha for testing H naught, theta is theta naught, against theta is not equal to theta naught, and that test looks like we reject H naught if the maximum of x1, x2, xn is greater than theta naught, or maximum of x1, x2, xn is less than or equal to theta naught alpha to the power 1 by n, and accept otherwise. So, this is the test which is unique, uniformly most powerful test for testing theta naught against theta is not equal to theta naught.